Assalamualaikum. My name is Mika Anik Faizal with the matrix number 230833, and I will be opening this video with our introduction. So, Euler's rule is a fundamental numerical technique used to approximate solutions to ordinary differential equations by estimating the slope at the beginning of each step. Although it is less accurate than Runge-Kutta, Euler's rule is still quite more simpler, and it serves as a more useful tool for understanding basic system dynamics. For this ENG3002 assignment, we decided to use Euler's rule to model the trajectory of a small drone during wind tunnel testing, concentrating on its motions in the first few milliseconds after the launch. This early stage is crucial as it provides key insights into the drone's initial flight behavior, which is essential for refining stability and control systems. So even with its limitations, Euler's rule can still offer valuable approximations that can support design and performance optimization of aerial drones, contributing to progress in aerospace engineering and autonomous flight technology.
Hi, my name is Nur Fatihah binti Fauzi. My matrix number is 230537, and today I will be presenting about the engineering problem. So in this report, the engineering problem focuses on how drones slow down right after it launch. The early motion phase is important because its effect on how stable, controllable, and efficient the drone will be during flight. The drone slowed down due to drag, which is the air resistance acting against its motion. To understand it better, the drone is tested inside a wind tunnel. A wind tunnel is a large tube where air flows around an object, simulating a real-life flying experience. So, the analysis is simplified by only considering the horizontal motion. Vertical forces like gravity are ignored. The drone horizontal velocity is described by a first-order differential equation, that is dvx over dt equal to negative 0.2 in the bracket vx plus 2. The drone starts with an initial velocity of 5.0 meter per second. To solve this equation, our team chose Euler method by using a time step that is h equal to 0.15 second. This method provides an estimate of how the velocity decreases over time. Understanding this motion also helps improve the drone design and performance during the launch phase.
Hi, my name is Siti Mariam Hidayah binti Muhammad Yusof, and my matrix number is 231341. I will be presenting about the numerical solution by using Euler's method. Euler's method is a numerical technique used to approximate solution for first-order differential equations when analytical solutions are difficult to obtain. In this case, the equation used is dvx over dt equal to negative 0.2 multiplied by vx plus 2. The horizontal component of velocity, or Vx, is affected by air resistance during the projectile motion. The term plus 2 within the equation represent an additional offset, such as wind, and the negative coefficient indicates a decelerating force acting on the object. The initial velocity used in this case is 5 meter per second with a time step h equal to 0.15 seconds. The Euler's formula used in this case is Vxn plus 1 equal to Vxn plus hf. This formula updates the velocity iteratively by taking the current velocity and adding the product of the step size and derivative function evaluated at that point. Each updated value serves as the starting point for the next iteration. This process is continued until the velocity sufficiently becomes small, indicating that the object has nearly come to a stop due to the drag. The velocity values shown in the table decrease progressively with each time step, illustrating the gradual reduction of motion caused by the air resistance. This numerical approach effectively demonstrates how drag impacts projectile motion over time.
So I My name is Vinoshan Gunalan and my metric number is 230554. So now I will briefly explain the analytical solution for our problem, which is about modeling the horizontal motion of a drone affected by air drag in a wind tunnel. So we begin with the first order differential equation that models the velocity of the drone, which is dvx over dt is equal to negative 0.2 multiplied with vx plus 2. This equation tells us the horizontal velocity decreases over time because of air resistance. To solve this analytically, we use the integrating factor method. First, we rewrite the equation in a standard form, which is dvx over dt plus 0.2 multiple with vx is equal to negative 0.4. Then, we find the integrating factor, which is exponent to the power of 0.2t. Next, we multiply the entire equation by this factor and it becomes a perfect derivative. This allows us to integrate both sides easily. After integrating, we solve for vxt, the velocity function. We also apply the initial condition to find the constant, which is when the t is equal to 0, the vx is equal to 5. By substituting this into our solution, we get the final analytical formula, which is vxt is equal to negative 2 plus 7 exponent to the power of negative 0.2t. So this equation gives us the exact velocity of the drone at any time under air drag. So in comparison to the numerical method, the analytical solution is more accurate, but only works when the equation is simple and solvable. So for more complex problems, we rely on numerical approaches like Euler's method. So that's all from me. I will pass to the next person. Thank you.
My name is Mama Sarah binti Mat Sazali with the matrix number of 230990. I will talk about the comparison between the numerical and analytical calculation methods. The difference in the Vx value between the two calculations method can be detected clearly by calculating its absolute error taken. For example, when t is equals to 5.1, we will get 0.039 as the absolute error. We can then calculate the relative error, in which we will get 7.44%. But then, if we were to plot the error against time, we will notice an increase of the error value as the time increases. As we can see from the calculations, we can analyze that the numerical method approximates a close value of the analytical Vx value. Its accuracy can be increased by decreasing the step size, h equals to 0.15, the maximum error over the 5 seconds interval is acceptable. Therefore, as analytical methods are often unable to handle complex problems, the numerical methods can be used as a replacement. This is because it can easily adapt to complex problems. However, in order to ensure a better approximation, the typical step size h should be 0.001 to 0.01, which will require a longer calculation step.
So to conclude, the ENG3002 assignment used core engineering mathematics to simulate the trajectory of a small drone during the initial milliseconds following launch in a wind tunnel. We developed a mathematical model of the drone's motion by representing forces such as drag and gravity as a set of ordinary differential equations. So with this, we used Euler's rule and achieved approximate numerical answers, demonstrating how even simple numerical methods may connect theoretical models to real-world problems. Our findings emphasize the necessity of precise initial circumstances in short-term trajectory predictions and show how mathematical techniques can help drive innovation in sectors such as aerospace, robotics, and autonomous systems. That's all from us. Thank you.